the liquid reality loophole, superfluid vacuum hypothesis. To understand the ripples, we need the pool. Get this, the proposal isn't that space is filled with some Victorian ether. It's that spacetime itself could be a quantum condensate, a ground state that formed when the universe cooled, and everything we call a particle is just a ripple moving through it. In a superfluid, you don't carry the fluid with you, you excite it. That's the loophole. If the medium is the geometry, you can't feel a wind because you're already inside the flow. Start with the map. In liquids at low temperature, you get a clean divide, a quiet background and excitations riding on top. Phonons, the sound waves, act like massless modes. Rotons behave like heavier, more intricate ripples with a gap. The analogy isn't cute, it's operational. If spacetime is a condensate, photons could be phonon-like excitations, while massive fields play the role of the gapped modes. The language of hydrodynamics, dispersion relations, effective metrics, suddenly reads like a Rosetta Stone for field theory successes with a twist. The stage is emergent. Here is where Volovik changes the stakes. He points to Fermi-points in momentum space, topological features where energy bands touch. Near those points, low-energy excitations behave like relativistic fermions. The protection is topological, which means small deformations of the underlying liquid don't break the illusion of special relativity. You get Lorentz symmetry as a low-energy miracle, not a microscopic commandment. That thread pulls two ways. It explains why Michelson-Morley didn't see a preferred frame. The symmetry's robust where we live. And it hints that at very high energies, tiny cracks could appear. Dispersions that bend, speeds that depend on frequency, signatures most experiments can't touch yet. Stakes spelled out. If gravity, inertia, and light are emergent fluid dynamics, the constants we treat as sacred, c, g, even Planck's constant as an effective scale, could be environmental properties of the condensate. Change the temperature or the density profile and the same laws might slide. That possibility doesn't just rewrite textbooks. It changes engineering. Flow profiles become design variables. Boundaries and defects become tools. But to earn any of that, the idea has to pass the gauntlet. No forbidden wind, no cheap violations, and no hand-waving where numbers should be. Action, not just talk. Physicists began chasing a medium that refuses to declare a rest frame. They looked for places where emergent symmetry might blink. High-energy cosmic rays that shouldn't survive if dispersion curves tilt. Neutrinos sprinting across galaxies with energies that would amplify the tiniest Lorentz cracks, yet arriving on time within wild precision. Constraints piled up. Meanwhile, theorists kept building models where the condensate's microstructure hides itself, the way water looks continuous to a surfer until you zoom to molecules. The bet was simple: low-energy blindness, high-energy honesty. What nobody knew at the time was how practical the analogy would become in the lab. Hydrodynamic equations can be rewritten to look like waves moving in a curved spacetime, an effective metric. Arrange a flow with a horizon, faster than the local sound speed on one side, slower on the other, and phonons behave like trapped light. That's not hand-waving. It's a blueprint that would later let teams pull Hawking-like thermal spectra out of Bose-Einstein condensates with tunable horizons. But we're getting ahead of ourselves. Back to the loophole's core claim, inertia. If the vacuum is a superfluid, maybe an object's mass isn't an intrinsic weight but a measure of how hard it is to disturb the medium's ground state. Push on the object, you couple to the background. The resistance you feel is the liquid's response. Mach's old whisper, mass tied to the rest of the universe, sneaks in as a non-local property of the condensate. It's elegant, but elegance doesn't earn a pass. The equations have to reproduce the equivalence principle and general relativity's precision where it counts, or it's a story, not a theory. Parallel action. The constraint that guards the door is Lorentz symmetry. If there's a medium, it can't prefer a direction the way a breeze does. Volovik's topology gives you that shield at low energies. The trade-off is predictive power at the edges. The condensate could disperse high-frequency waves, alter group velocities by parts in 1020, maybe twist polarization in intense fields if the microstructure breaks certain discrete symmetries. Those are tiny, but not untouchable. Set an agenda. Chase dispersion with gravitational waves, polarization with vacuum birefringence hunts, and any sign that the liquid carries quantized defects the sky might betray. Human stakes land here. A theorist spends a decade refining models that, by design, refuse to give you a headline-grabbing crack. An experimentalist spends nights lowering noise floors to measure a phase shift so small it feels like cheating. They both need the other. The loophole only lives if the lab can't close it, and the lab only cares if the math draws a target. This was the moment everything changed for our story. We weren't asking if space had stuff in it. We were asking if stuff is what space is. If the answer is yes, then ripples, horizons, vortices, and boundaries aren't metaphors. They're the language reality already speaks. And if the answer is no, the hunt will still have taught us to hear the vacuum more carefully. But if there's a medium, it should ripple, and ripples leave fingerprints. Ripples in the medium, gravitational waves versus fluid waves. If the pool is real, it should ripple. And when the first direct detections of gravitational waves hit, the world heard spacetime ring like a drum. Two black holes collided, and the distance between mirrors on Earth stretched and squeezed by less than a proton's width. The signal was clean, matched templates from general relativity, and arrived at both detectors with timing that left little room for anything but waves traveling at light speed. If spacetime is a condensate, those ripples are the medium talking. The question is how. Stakes first. In a fluid, waves can disperse. Different frequencies travel at different speeds. They can attenuate if the fluid has viscosity. A true superfluid, though, delivers almost no dissipation. Sound can fly without dying. If gravity's waves ride an emergent medium, their speed might drift with frequency or their shapes might smear. Unless the liquid hides its microstructure so well that, at LIGO's band, the waves look exactly like Einstein's geometry. The bet is precise. Any tiny frequency-dependent lag, any loss, any deviation from C would be a smoking gun. Action: what actually happened in the data? With dozens of detections in hand, LIGO and Virgo stacked events to test dispersion. They asked if high-frequency parts of the chirp got ahead or fell behind. The bound slammed tight. The graviton's Compton mass, if you insist on thinking that way, sits below roughly 10 eV, and the phase evolution matches non-dispersive propagation over hundreds of megaparsecs. Meanwhile, a landmark binary neutron star event delivered a gift. Photons from the kilonova trailed the gravitational waves by about 1.7 seconds after a journey of over 100 million years, with messy astrophysics in the middle. That pinned the relative speed difference between gravity and light to tiny parts in 1015, 1060. If there's a fluid, it didn't slow the waves down. Parallel action at the opposite end of the spectrum, pulsar timing arrays. These teams listen to millisecond pulsars ticking across the galaxy and look for nano-Hz gravitational waves stretching the interval between beats. Collaborations have reported a common spectrum process with angular correlations that look like a background hum of supermassive black hole binaries. That's a different medium test. Across light years, is there dispersion or damping? So far, the background strain spectrum leans toward what you'd expect from huge binaries, not a sticky fluid. No obvious viscosity, no frequency cutoff screaming microstructure. What nobody knew at the time the detectors turned on was how constraining silence could be. Superfluids promise low dissipation, which helps. Near zero viscosity means waves don't die as they travel, but dispersion is the sharper knife. If the condensate's microphysics breaks Lorentz symmetry at high frequencies, group velocities can bend. Cosmic rays already cornered that possibility by not losing energy via forbidden processes. Gravitational waves now add their weight. Within the bands we can hear the medium, if it exists, doesn't betray itself. This was the moment everything should have closed, but a door stayed cracked. Emergent symmetry buys you protection at long wavelengths. High-frequency cracks can hide beyond today's ears. LIGO listens from tens to a few thousand hertz. Pulsar arrays hear whisper low notes. In between sits LISA's future band, millihertz waves from galactic binaries and massive mergers, the region where a condensate's dispersion, if any, might rise gently before it spikes. And above LIGO, third-generation detectors aim for earlier inspirals and sharper phase tracking that could shave another order of magnitude off dispersion bounds. Human stakes make this real. In a control room, an analyst stares at residuals, the tiny difference between data and template, wondering if a wiggle is astrophysics or a clock glitch. Across the hall, a theorist mutters through a mouthful of cold noodles that superfluid viscosity should be effectively zero, then scribbles a correction term that would alter phases by 1 part in 1019. The analyst shakes their head. We're not there yet, the theorist nods. But that's the target. Meanwhile, the viscosity question turns from fear to feature. A superfluid vacuum would let waves cross the universe almost losslessly, which is exactly what we see. That's good for the liquid camp. Dispersion remains the knife's edge. If even a tiny frequency dependence turns up, consistent across events, scaling with distance, surviving calibration, it would be hard to fold neatly into pure geometry. It would smell like a medium. Impact right now. LIGO's success doesn't kill the liquid, it cages it. Any condensate must mimic general relativity to exquisite precision across huge baselines, with emergent Lorentz symmetry holding firm where we can test it. Pulsar timing adds weight at the opposite end. The sky says, if there's a liquid, it's superfluid and shy. No viscosity we can see, no dispersion we can hear, yet. While that was happening in the data rooms, a different idea brewed. Waves are gentle, but vortices shout. If a superfluid vacuum exists, it might host quantized swirls, topological defects with gravitational fingerprints the cosmos can't completely hide. Vortices, quantization, and the cosmos. Waves are polite, vortices aren't. In every true superfluid, swirl the liquid hard enough and it refuses a messy eddy. Instead, it snaps into quantized vortices, discrete tubes of circulation with fixed strength. That's a smoking gun. If the vacuum is a condensate, the cosmos might carry its own quantized swirls, defects written into space itself. They wouldn't look like little whirlpools. They'd act like heavy, string-like scars stretching across regions of the universe, tugging on light and matter with signatures gravity can't fake easily. Stakes first. Detect a vortex, tag the medium. A direct imprint of quantization would push liquid reality from suggestive poetry to something you could hang a career on. These aren't small stakes. They'd touch cosmology, particle physics, even the way we measure mass on a satellite. And the risks cut both ways. If we keep not seeing them, the liquid's allowed parameter space shrinks to a pinhole. The story gets leaner or it collapses. Action, what we looked for. In the sky, the closest analogs are cosmic strings and other topological defects predicted in a range of high-energy models. They bend spacetime in a peculiar way, not like a lump of mass, but like a wedge cut out of the plane. Light passing on either side doesn't curve gradually. It splits paths around a conical geometry. The tell is lensing, pairs of identical, undistorted images separated by a fixed angle, no magnification gradient, no swirling arcs. Workers combed galaxy surveys for those twin-stamp pairs. Teams ran algorithms over billions of sources, flagging candidates for follow-up. Meanwhile, the cosmic microwave background offered another window. A string network would leave step-like temperature discontinuities and specific B-mode polarization patterns, like faint stitching across the oldest light. Parallel action. Theorists mapped superfluid vortices onto these defects. In a condensate, circulation is quantized by Planck's constant and the mass of the excitations. Translate that to an emergent vacuum and you get tension and core sizes that depend on the microphysics. The key is topology. If the condensate's order parameter wraps non-trivially around some symmetry space, you must get stable lines or walls. No way to unwind them without tearing the whole field. That's why strings became the hunting ground, a robust prediction of many broken symmetries, and a neat place for a liquid-like vacuum to hide its swirls. Impact so far, constraints tight. The Planck satellite and ground-based CMB experiments squeeze the allowed string tension. If a network exists, it's faint. Lensing surveys knocked down the odds of bright, simple pairs. The sky didn't deliver a headline string, but no headline is no hint. A handful of peculiar alignments punched above their weight. In one case, a ring-like pattern around a galaxy cluster popped in a pipeline, clean, symmetric, and for 1 electric hour looked like a textbook defect. Microstory. It was near midnight when the team's Slack lit up. A postdoc, eyes fried from scrolling stamps, typed, "I think we've got one." Coffee brewed, code reran, and the room leaned in. On reanalysis, subtle shear from nearby structure unraveled the ring. It dissolved back into ordinary lensing. The channel went silent except for a single sigh emoji. Hints remained, decisive proof didn't. Meanwhile, a different vortex angle teased the story from another side. Galaxy rotation curves. It's tempting, too tempting, to say a swirling medium could support persistent circulations around galaxies, reducing the need for dark matter. The metaphor writes itself, quantized vorticity giving flat curves. Here, S where it gets dangerous. Hand-waving runs into numbers. Rotation profiles aren't one size. They vary with mass, morphology, environment. The successes of the dark matter framework, lensing, structure growth, the CMB acoustic peaks, don't vanish because a liquid metaphor sounds good. If a vacuum condensate contributes, it has to either mimic a cold, collisionless component with precision or reveal new small-scale signatures that we can actually catch. So far, claims that vortex-supported flows solve rotation curves haven't survived the gauntlet. The liquid camp learned a hard rule. Analogies motivate, data arbitrate. What nobody knew at the time the string searches matured was how sensitive boundary conditions might be. In superfluids, vortices like to pin. Edges, impurities, places where the order parameter changes. Translate that to the universe and you ask where the vacuum's order parameter could vary. Phase transitions in the early universe would do it. Domains cooling into different orientations. Seams where they meet. The CMB is our fossil map of that freeze. If a superfluid vacuum gelled through a transition, relic line defects might lace the sky, yet diluted by inflation or washed by later dynamics to the threshold of our instruments. Human stakes again. Observers live with the fear of false hope. Every candidate costs nights and pride. Theorists live with the fear of overpromising. Every elegant sketch invites a demand for a number you can check. The liquid narrative survives here because it keeps finding ways to be precise. Predicted lensing geometries, polarization templates, statistical footprints you can falsify. Impact today. Surveys like DIS, HSC, and soon Euclid and the Rubin Observatory keep pushing. Null after null squeezes parameters. That's science doing its job. If vortices exist, they're either rare, delicate, or dressed in clothes we haven't recognized yet. The medium, if real, plays shy with its quantization. While the sky stays murky, one lesson sharpens. In fluids, vortices love edges. If cosmic space is a condensate, maybe you don't start with the whole sky. Maybe you go where boundaries are clean and under your thumb. When the sky is murky, tabletop the labs, analog gravity and synthetic spacetimes. When the sky is murky, you bring gravity to heel on a bench. That sounds absurd until you watch a cloud of atoms drop to billionths of a degree and start behaving like a single quantum thing. In a Bose-Einstein condensate, sound becomes a first-class citizen. And with the right flow, sound waves see an effective geometry, an acoustic spacetime.